So now that we've generated our posterior predictive distribution of datasets by simulating using parameter values sampled from our MCMC analysis, we need a way to quantitatively compare these simulated datasets to the empirical data that we've collected. And this is the role of test statistics, or a suite of test statistics. So a test statistic is just a numerical value that summarizes some aspect of our dataset and allows us to compare across different datasets. Now, there's no single correct test statistic to use for posterior prediction, and the types of test statistics we're going to use are going to vary a lot depending on the kind of analysis we're doing, so the kind of data we have and the kind of model we're assuming. So here we're going to try out 4 different test statistics, and for now we're just going to say these have been picked essentially arbitrarily. So we're going to look at the first percentile, so what value for any given data set, where does the first percentile of those trait values lie? What's the median trait value for that data set? What's the mean trait value? And what's the 90th percentile? And we'll compare the answers we get at the end using these different test statistics and ask if they all give us the same answer or different answers and what that means for our interpretation of the results of posterior prediction. But again, these test statistics here, these are just numerical values that capture some aspect of our data set. So to actually calculate these values in RevBayes for this example, first, sorry, to scroll back up real quick, because each of these values depends in some way on the order of our trait values, we want to make sure our trait values are already in order from smallest to largest. And so what we're going to do is we're going to sort each of our data sets. So here we're using a for loop, and we're going through each of our simulated data sets, and we're sorting the values in that simulated data set and then just resaving it in our original SIMS vector. And then we're going to do the same thing for our empirical data set. We're just going to sort the values so we know that they're in order from smallest to largest. Now, a couple of the statistics that we're interested in, actually 3 of the 4, require us to be able to calculate a percentile. Now, there's no built-in percentile function in RevBayes, but thankfully there's a way to write your own functions in the Rev language. And so we're going to take advantage of that capability here. So we've defined our own new function that we're simply calling percentile. And this function will return to us the number that we're interested in. So this this will return to us the percentile we're interested in based on the values that we provide. So p, the argument p to this function is the percentile that we're interested in, and this nums vector here is the trait values, the actual data set for which we're calculating this percentile. So we'll use this function, this custom function here in just a minute. So first we're going to calculate each of our 4 test statistics for our empirical data set. So we're going to calculate first the mean of our empirical data set. Next, we're going to calculate the median of our empirical data set. Then we're going to calculate the first percentile of our empirical data set. And then the 90th percentile of our empirical data set. So you'll see for these last 2 values, again, we're using this built-in percentile function that we just created. So we're passing it first the percentile we're interested in, and then the data set for which we want to calculate that value. And then next, we're going to go and we're going to calculate each of these same test statistics for each of our simulated data sets. So we're going to create 4 different vectors here. One to hold the means of our simulated data sets, the medians of our simulated data sets, the first percentiles of our simulated data sets, and the 90th percentiles of our simulated data sets. And again, we're going to use a for loop to loop over all of our simulated data sets, calculate each of these values, and then store them in the relevant vector. And so once we've done that, now we have the set of test statistic values that are reasonable given the model, so the posterior predictive distribution of test statistic values. And then we've also got the corresponding test statistic values for our empirical data set, and so now we can compare them.